Hello everyone. After all this tensor analysis video, today we'll start like how will we apply those tensor notations and indices in real physics scenarios. So we'll start today. Special relativistic particle dynamics. Okay, special relativistic particle dynamics. So first thing we'll see here is our four velocity. First thing we'll see here is our four velocity. Okay, so in a covariant formalism, one can construct a four vector whose spatial components are proportional to the components of three velocity of a particle, that is, or vx, vy, vz, and the temporal component is proportional to the speed of light. That is, the zeroth component is called the temporal component. Okay, this is the zeroth component, which is just proportional to speed of light, and the other spatial components are proportional to the three velocity. Okay, so contravariant projections of the four velocity, we can write the contravariant projections, of this four velocity, or it's also called wild velocity vector, or velocity vector wild velocity vector. We can write the projections, we can write as u contravariant alpha is equal to dx alpha divided by d tau. Okay, yeah, which can also be written as dx alpha divided by dt by gamma. So d tau is your this time dilation kind of thing. Time dilation, if you remember, gamma is your what? Gamma is a simply 1 by root over of 1 minus v square by c square. Okay, if you remember. Okay, and this is your dt by gamma, d tau. Okay, so dx alpha divided by dt by tau, dt by gamma. So gamma goes up, so it will kind of become it will become dx alpha divided by dt. Okay, so I can write this like I can write like this: gamma of this is d, this is the zeroth component, temporal component, and along with it the xyz components. That is, I will denote it as I, where I is your what? Xyz. Okay, and this can also be written as gamma is your, this is your c. Okay, and this is your simply v vector that we usually write in three dimensional. Okay, vx, vy, vz. Right, I means your 1 2 3, which is your x1, x2, x3, x1, x2, x3, which are your what? XYZ actually. Okay, yeah, and dx naught by dt, as I written here, is proportional to c, or like directly c, and this is your v vector. Okay, so this is your u alpha, the contravariant projections of four velocity. Okay, all right, all right. So next is, since the prop, this is tau is your what? Tau is your actually is your proper time in relativity. We know this is your proper time. Yeah, and it is invariant under Lorentz transformation. Invariant under Lorentz transformation. Invariant under Lorentz transformation. All right. So the four velocity u alpha transforms like the coordinate differentials dx alpha. Okay, under your Lorentz transformation. Yeah. So we can write that point also. Four velocity u alpha transforms like transforms like the coordinate differentials What are they? When if it's dx alpha under Lorentz transformation, I will write Lorentz transformation as LT. Okay, Lorentz transformations. So let's calculate the norm. The norm of u alpha will be what? It's an universal constant. Norm of u alpha, I will, if I calculate norm of u alpha, okay, which is positive. That means, so norm of u alpha will be what? U alpha covariant into contravariant, and they will give me, if I write this thing, gamma, what, gamma cv. So it will give me gamma square c square, okay, minus v square, right? This is your um, this is called time like 4 vector. Okay, this is called your time like 4 vector. This is called your time like 4 vector, all right? And this is, okay, this is actually equal to c square, yeah, which is greater than 0. How is it equal to c square? Because we know gamma is what, 1 by 1 minus v square by c square root over. So if I put it here, if you see 1 by minus v square by c square, and this is eventually v c square minus v square. So this becomes 1 by, this is c square goes up, c square minus v square, and this is a c square minus v square. So it is eventually c square, which is greater than 0. Okay, so this is your what? This is norm of u alpha. Okay, norm of anything we calculate norm of a alpha, suppose. So a alpha into a alpha, like that. This is called a norm. Okay, we have studied this in tensor. So everything we are going to study is just application of tensor here. So this was your what? 4 velocity, right? Exactly like that we'll study now 4 acceleration. 4 acceleration. 4 vector we have studied already, right? Now it's 4 acceleration. Okay, we'll study now 4 acceleration. Okay, let's see what is 4 acceleration. So again, in a covariant formalism, we can say 4 acceleration. Again, it can also be called world acceleration vector. Okay, 4 vector, world vector, 4 velocity, world velocity, 4 acceleration, world acceleration. Okay, rate of change of 4 velocity. Simple. So this is your rate of change of 4 velocity. So I can write a alpha is equal to du alpha by d tau. Again, exactly like this, the way I wrote here, that u alpha is a rate of change of 4 vector, okay, 4 position vector, dx alpha by d tau. Again here it is du alpha by d tau. Again d tau, in place of d tau I'll put what? D tau is a proper time, so I will put dt by gamma. Okay, so gamma will go up, gamma du alpha divided by dt, yeah, du alpha divided by dt. So I can write this as gamma, okay, du alpha divided by dt. What is u alpha? U alpha is your gamma cv, right? U alpha is your gamma cv. So I can kind of write that d by dt of gamma c and v, right? So I have to do something there. So if I do it properly, I will get what? See, a gamma of d by dt. See this properly, it's gamma c and this is gamma v, right? So I will take the derivative on both, yeah. So gamma, this becomes gamma dot c, because c is a constant, but here gamma and v both are variables, so I will do product rule. So gamma dot v vector plus gamma v vector dot, yeah. Is that correct? Is that correct? So this is your what? Acceleration 4 vector, okay, or 4 acceleration vector, or 4 acceleration whatever. Gamma dot c, sorry, gamma dot c, gamma dot v plus gamma v dot, yeah. This is a 4 acceleration, okay, yeah. Okay, now let's calculate what is gamma dot. We just cannot leave it like this. Okay, gamma dot, we can say that d by dt of gamma. Okay, so d by dt of 1 by root over of 1 minus v square by c square. Yeah, so c is a constant. So we can kind of do this d by dt of c by root over of c square minus v square, right? So c will go out, c will go out. Um, Otherwise, we can do another way. Like, mm, okay, okay, wait. We can do another way here. Wait, this will get complicated. So we will do one thing. Okay, d by dt of gamma is what? Okay, 1 by root over 1 minus v square by c square. I can write this as d by dt of 1 minus v square by c square to the power minus half. Correct? To the power minus half. Alright. Yeah. So, what will I do? V square. What will I do with v square? I will write it as v dot v. Okay. So let me write it again. D by dt of 1 minus v dot v by c square minus half. Alright. So let's do the derivative. Um, if we do the derivative, so minus half 1 minus v dot v by c square to the power minus 3 by 2 into this derivative. Derivative of this one will be 2, okay, v dot v and some dot here divided by c square. I hope you understood. Yeah, and there is another minus here. So minus 2, 2 cancelled out, this cancelled out. So what we are getting here is minus 1 minus v dot v by c square to the power minus 3 by 2. This is v dot divided by c square. This is the product rule applied here, okay, after derivative. Okay, now this can be written as gamma to the power 3, right? Yeah, because gamma is a to the power minus 1, but this is minus gamma cube, and this is a v dot divided by c square. So that was my purpose to do it this way. So what will I do now? I will just simply, in place of the gamma dot, I will put it. Okay, so a alpha is equal to what we had got. A alpha. A alpha is what? Gamma gamma dot c. This is gamma dot v plus gamma v dot. So in case of gamma dot, we'll just put this one. So gamma q v dot v by c square into c, and this is your gamma dot q v dot v dash v dot v dot. Okay, I'm missing a dot here. Divided by c square into v plus gamma into gamma q, that is gamma fourth. Okay, v v dot by c square again v dot. All right. Yeah. So what will come of this? This is c. Yeah. Okay. So if I write final expression, I will get what? C v dot v will become like what? What will it become? Okay, no. Leave it like that. Leave it like that. Okay, I will just write the final expression for it. Okay, so gamma square. I will take one gamma out. Okay, so gamma square. So this becomes gamma square. Yeah, v dot divided by c, and this one will become, okay. This one will become uh, this one will become. I'll just write it. Okay, v dot plus gamma square. You can easily solve it, no problem. I've done up to this point. You can solve it after this. By c square into v. Okay, so this is your a alpha. You don't need to memorize it. You need to be able to solve it when asked. Okay, so one may explicitly verify. You can explicitly verify the following 2 points also. If I explicitly verify, what first will be a alpha will be less than 0. Okay, that is what? A alpha is a space like 4 vector. So space like A alpha is a what? Space like 4 vector. Okay. Space like 4 4 vector. Acceleration 4 vector or anything. Okay. Next point will be, next is what? A alpha U alpha. Suppose if I write A alpha U is a velocity 4 vector, will always be equal to 0. Okay. Because why? Because A alpha U alpha are orthogonal to each other. Okay. They will be orthogonal to each other. Correct? Yeah. So whatever things are done now, for velocity is done, for acceleration is done. Okay. Yeah. Next. Next is a what? Next is a for momentum and energy. Number three, for momentum, velocity, acceleration, now momentum. For momentum and energy. Again, we will take it in a covariant formalism. We can define for momentum of a particle as what? The product of a particle's rest mass and its for velocity. So fourth thing is always involved here. So it can be written as what? Product of rest mass m and your what? For velocity, which is your u alpha. Correct? For velocity is your u alpha. So the spatial coordinates of this four momentum corresponding to what? Correspond to those for relativistic three momentum again, and the temporal component is proportional to the relativistic energy. Okay, so we can write that. So the spatial components, spatial components of four momentum correspond to what? Correspond to relativistic three momentum. Relativistic three momentum of the particle. Relativistic three momentum of the particle, and the temporal component, and the temporal component of four momentum will be correspond to what? Is proportional to, is proportional to the total relativistic energy. Total relativistic energy. All right. Total relativistic energy. Yeah. Okay. So the contravariant projections of the four momentum, if I write the contravariant, the contravariant projections of the four momentum, contravariant projections of the four momentum, but it will be let me write p alpha. Okay, p alpha will be what? As I said, rest mass into your four velocity m into u alpha. U alpha is what? Dx alpha by d tau, which is proper time. Yeah, dx alpha by d tau. So we can write this as gamma mc mc comma m v vector. Correct? Yeah. So gamma will go in gamma mc gamma m v vector. Yeah. So this gamma into m I can write it in a capital M fashion, like mc. Okay, like this. All right, capital M. It's a bit different, and we can write this as, we know E is equal to mc square, right? So mc can be written as E by c. See, temporal component is proportional to the total relativistic energy E, and mv can be simply your momentum vector. Yeah. So this is your p alpha. Okay. So this gamma m is a what? This is your relativistic mass. Relativistic mass. Okay. This, and this mv. This mv is a what? Relativistic momentum. Stick momentum. Relativistic momentum. Okay. Three momentum actually. Relativistic three momentum, because this is the temporal component is taking away the other one. E is your mc square. This is a relativistic mass into c square. So gamma m into c square. Okay. So this is relativistic total energy. That is rest plus kinetic. Okay. This is both the rest plus kinetic. Right. Yeah. So the above interpretations of P and E, okay, P and E are justified. Okay. And how? How they are justified? So we will expand the power of P and E in powers of V by C, and we'll find the in non-relativistic limit, that is V by C is almost equal to zero. So what will we get? We will get P approximately equal to small m into V, and E is equal to mc square plus half mv square. This is completely non-relativistic. Okay, non-relativistic case. What is non-relativistic case? V by C almost equal to zero. Okay, this is not very negligible. V will be like 20 meter per second C. So this is completely negligible, right? Yeah. So P and E are actually functions of V whose conservations are Lorentz invariant. Okay. Conservation should be always Lorentz invariant. That is, conservation of P under a Lorentz invariance, a Lorentz transformation, necessarily implies that the conservation of E is also there. Okay, so write this very important point. That, conservation of P under a Lorentz transformation LT. Okay, I'm writing as LT. Necessarily implies necessarily implies necessarily implies the conservation of E. Necessarily implies the conservation of. Okay. All right. So how? Okay. So let's see. Okay, let's calculate the norm as we have calculated in the previous cases in place of acceleration velocity. Norm of the four momentum. Norm of the four momentum. Okay. Norm of the four momentum. So let's see. Norm will be P alpha go into contra. Okay. So P alpha can be written as alpha beta P alpha, this P alpha and P beta. So eta alpha beta and P beta will give me P covariant alpha. Okay. So this can be written as eta 00 P 00 plus what? Eta ij P ij. I can be 1, 2, 3. Yeah. Alright. So I can write this as eta 00 is a what? Hmm? So this is P0 square. Eta 0 is 1. So this will give me P0 square plus eta ij Pij. Okay, P0 square is your simply E square by C. E by C. So E square by C square. And this will give me what? Eta ij. Eta 1 1 is minus 1. Eta 2 2 is minus 1. Eta 3 3 is minus 1. Okay. And other things are 0. Eta 1 2 is 0. Eta 2 1 is 0. Other things are 0. Yeah. It's like delta ij. Na? Delta ij. So we can write, like, we will get the components P is 1 1, P 2 2, P 3 3. Okay, and that can be written as P square. Okay, so this is your norm of the momentum 4 vector. Right? Yeah. So if I expand it a bit, if we expand it a bit, like, we can also do this. P alpha is equal to m square u alpha. We can do that. right? Because how? Because P alpha is your what? M U alpha. This one is your M U alpha, like this. So we can just multiply M square U alpha. So M square. What is your U alpha? U alpha we know is gamma square C square minus V square. Right? Gamma square C square minus V square. So in the end, this is M square into 1 by 1 minus V square by C square. C square minus V square, and this can be C square cancelled out. So M square C square. Okay. So this is your P alpha. P alpha. The norm can be also M square C square. Okay. Yeah. Got it. Yeah. So PL. This is equation two. You can give equation two. This is what we got. Equation one. So equating equation one and two. See P alpha this. P alpha this. So equation one and two. Equation one is equal to equation two. Like the left hand side. Okay. So the right side will also match. So E square by P square, E square by C square minus P square is equal to what? M square C square. So from that, E square minus P square C square is equal to M square C fourth. Isn't it a familiar equation? E square is equal to P square C square plus M square C fourth. This is where from this we got E is equal to M. So this is the origin. Okay. This is the origin. This is where we get it. We have studied so many times, we have applied, we have done numericals, but this is where it is coming from. Okay, you can see the direct proof of it. So suppose if it is asked, prove that E square is equal to P square C square plus M square C4 using 4 momentum. So we will use what? The norm of the 4 momentum, that is P alpha P alpha. The norm we will get like E square by C square minus P square. Then we can also put P alpha as M U alpha using the 4 velocity vector. P alpha contra M U alpha. So again, contravariant this one, and we can just take the norm again, and we'll get this. After equating these two equations, we will get this. So this is where we are getting this equation. E square is equal to P square C square plus M square C4. This is a very satisfying result. Like it's like coming to the origin. Okay, like where we started, we just came to that. So it's a very satisfying feeling, right? So this is your, yeah, norm. Now next is what? Next is we'll do conservation of energy and momentum. Conservation of energy and momentum. Okay, conservation of energy and momentum. So again, the 4 momentum is your P alpha transforms as a 4 vector under Lorentz transformation. Okay, and then okay, suppose okay, suppose there is a transformation. Okay, suppose if I write P dash alpha, P dash alpha, how will I transform it? I will use the this one lambda alpha beta, and I will do the P beta. So eventually I'm getting this P dash alpha. Okay, so suppose mm, suppose if I write like this, it's very different rotation. Don't worry, you will understand slowly. Summation. Okay, I'm taking the summation here. This alpha beta delta summation n, and this one P beta n. Okay, so I'm taking a summation. Okay, so the conservation means what? Conservation of 3 momentum P under a Lorentz transform means what? So conservation of the relativistic relativistic 3 momentum three momentum p vector or under a Lorentz transformation, under a Lorentz transform means, what does it actually mean? It means that this thing should be zero in one inertial frame, in one inertial frame, and that will imply that the other thing should also be zero. That is the meaning of conservation in all other inertial frames. Yeah. So this is the meaning of them being conservation, like conserved, right? Yeah. Yeah. In the mass case, also the same goes for the mass case. Okay. So we'll not get into that. We'll not get into the proof of it. Okay. Okay. Next is your we will do an application of whatever we have studied. We'll do an application, that is a Compton effect. How all of this will be useful in Compton effect. We have derived Compton effect in quantum mechanics, but this here we will do it in our relativistic way. Okay. So let's write on Compton effect. Compton Compton effect. Okay. So particle coming in, hitting another particle, and these are the two directions. This is the recoil. Okay, this is the initial energy EI, final energy EF. This is the mass, and this is the angle at which it is going away. Okay, so a photon hits a stationary particle of rest mass m. So we need to determine what the angle of deflection theta. We need to determine this theta of the photon in terms of what's its initial and final energy. Okay, we need to define that, and or its initial and final frequencies. Anything we can calculate. So this is your what? This is suppose figure one, illustration of Compton effect. Okay, so so initial and final four momenta first we'll write, and we'll do the conservation part. So suppose initial momenta is your what? P alpha I initial. Okay, or I suppose I. No. P alpha I. Let's take capital I because I can be anything also. P alpha final momentum is P alpha F. Okay, respectively of the photon. So P alpha I will be what? P alpha I will be your EI by C, comma PI. Okay, that's right. Final will be what? Final will be EF by C, and this is your PF. Yeah, all right. So here PI and PF are the initial and final relativistic three momentum. This is a see. This is used here. That means this is a three momentum. This is the temporal component, that is of zeroth component. So that is taking away one component. So this is the three momentum. Okay. So if I write about them, suppose, okay, um, for the photon EI is equal to what? C into PI, and the EF is will be C into PF. Okay. Now, like EI, we can write that C into PI. Every bit of step we will write EF is equal to C into PF. Okay. So now, uh, P alpha I, if I write P alpha I, P alpha I will be how much? It will be simply Pi magnitude, and this is a Pi. Okay, and P alpha F will be PF magnitude, and this will be PF. Okay, don't worry, we'll slowly go here. For the massive particle, its initial energy is equal to rest mass energy, right? Because it was at rest initially, then the photon hit it. So initial energy is the rest mass energy, that is mc square. Okay, so initial energy is equal to the rest mass energy. Initial energy is the rest mass energy, that is your small mc square. Okay, so its initial force momentum will be what? Initial force momentum, if I write force momentum, initial force momentum will be P alpha I equals to mc, and this is your, I will write it as zero vector. Okay, just wait, I will write it as zero vector, zeroth component. Okay, zero vector, and because it was at what? Rest. Okay, so this is the initial force momentum. This is for the photon, right? This is for the photon, this is the three momentum. Because it was at rest, so its initial momentum will be of course zero. Okay, this is for temporal component. This is for the photon. Photon doesn't have any rest mass, so it won't be zero. This one will be zero. Okay, so its final force momentum. Suppose final force momentum will be p alpha f. Okay, so that will be what? P alpha f. Suppose we will calculate the this one, norm of it. Okay, suppose norm of it. So it will be equal to the norm of the initial also. Okay, I hope you understand initial, because it's conservation. Conservation is there. So m square c square, simple. Because the mc, this is mc now. This is mc. So mc into mc, that is m square c square. So by the conservation of force momentum, by the conservation, just a minute, I will just connect the charger. So by the conservation of what? Conservation of force momentum. Conservation of force momentum will be p alpha I plus p alpha I. Okay, suppose p bar is equal to p alpha f plus p bar alpha f. So it will be giving me p bar alpha f. It will be given me f is equal to mc plus pi, okay, minus pf, okay, and this will be pi minus. Is that all right? Yeah. Okay. So if I calculate it now, p alpha f, p alpha f again. If I calculate the norm, okay, that will be m square c square. Yeah, m square c square is equal to mc plus pi minus pf square plus pi minus pf, okay, square. Yeah, so that will be equal to 2mc pi minus pf plus pi minus pf. Okay, is equal to what? Is equal to pi square plus pf square, f square plus 2 pi pf. Yeah. So is equal, that implies 1 by pi minus 1 by pf is equal to 2 by mc. Okay. 2 by mc sine square theta by 2. Right. Yeah. So where theta is the angle between, theta is the angle between P and PF. All right. So directly we can, if we do the all the things, we can get theta is equal to 2 sine inverse mc square by 2 h cut 1 by vf minus 1 by vi and half. Right. This is a Compton effect. Okay. Next is over. Next is a 4 force. Next write down. Next is a 4 force. Next is your 4 force. 4 momentum is gone. Now 4 force. Okay. So again 4 force will be what? The momentum's derivative. So if alpha will be dp alpha by d tau. So again gamma dp alpha by dt. Correct? We can write it directly E gamma of, sorry, gamma of E dot by C. This is F vector. Okay. Where F vector is what? F vector is again 3 momentum, 3 force we can say. That is dp by dt. Okay. This is called what? Relativistic 3 force. Now this is very easy now for you. You can easily understand. So I won't take much time. Relativistic 3 force. Right. So we can write F alpha is equal to m into a alpha. This is the relativistic 4 force. That is gamma m a alpha. Okay, which is gamma m d u alpha by dt. Okay, which can be regarded as a relativistic generalization to the Newton second. Okay, we can say that a motion. So this is kind of a relativistic generalization, relativistic forces, relativistic generalization of Newton's second law of motion. Okay. So for a particle moving with instantaneous velocity v, okay, the time derivative of total energy is what? Power. So power is what? Force into velocity. Power, I can time derivative, I can write E dot is equal to force into velocity. Right. So force can be written as the momentum dot velocity. Yeah. Okay. So F alpha, I can write it as gamma of E dot by C F vector is equal to gamma f dot v by c f vector. Okay. So since the components of flow velocity is what are what is u naught is equal to gamma c naught, so I can write f alpha is equal to 1 by c f dot u, and this is u naught f. Okay, so just make it a box. All right. I hope you understood all of this. If you have any questions, you can let me know in the comment section. Okay. So yeah, so this much for today. In the next class, we'll study the next section of this. That is your covariant formulation. Next class, covariant formulation, covariant formulation of electrodynamic equations. We'll slowly deep into relativistic electrodynamics, electrodynamic equations, Maxwell's invariance, Maxwell's covariance of Lorentz transformation. All of that we'll do. Okay, covariant formulation of electrodynamic equations. We'll study in that chapter. We'll study four current density. Okay, covariant Lorentz force equation. All of that. Okay, so yeah, that is it for this class. See you in the next class. Okay, yeah, thank you.